Okay, so we are going to move on with our lesson on matrices. So you saw we introduced the matrix in the last video, and it may have seemed a little strange as to why we were doing that, but the whole point of talking about systems of equations in this unit, in this matrix unit, is to use matrices to solve those systems. So we saw how to manipulate and operate with matrices, but now we're going to kind of turn it more towards one of the usefulness properties. I don't know how to talk. Useful properties of matrices. So we're going to go back, and I'm probably repeating myself a little bit from the last videos because it's been a while since I've looked at them. But I want to talk about, we're going to take some notes. So we're going to talk about, I'm going to create a system of equations. So, and I'm going to do that with a three variable system. So, should look familiar. X plus 2y minus 3z equals 4, whatever. 3x plus z equals 5. Negative x minus 3y plus 4z equals 0. So the first thing I want to talk about is when we're utilizing this process, when we are creating, when we're using a matrix to solve a system of equations, we want the equations that we're given to be in standard form. And that should ring a bell. It's just when we have these variables in alphabetical order, so x, y, z. So this second equation is missing y, but that's okay. If you want to put a 0 coefficient in for y, you can. But it should have all of the variables in alphabetical order. And then they should all be on one side of the equal sign. And then the constant is the only thing that should be on the other side of the equal. So 4, 5, and in this case 0 are on the other side. And then we have x, y, and z. So that's just standard form. So we want to make sure that this, all of our equations are in standard form. Or when we go to use a system go to use a matrix to solve a system of equations, it's going to get all screwed up and we're going to do a bunch of work for nothing. So the first term I want to talk about is a coefficient matrix. And that is literally exactly what it sounds like. It's just going to be a matrix made up of the coefficients of these variables. That's why standard form is important. So if I have 3 variables and 3 equations, my coefficient matrix for this system would be a 3 by 3. So I'm going to go and write my coefficients for the first equation. So 1, 2, negative 3. 1, 2, negative 3. And I'm closing that matrix. So I'm ignoring this because it's not a coefficient. A coefficient is the number that we multiply by a variable. So the second equation is just the 3, and the z has a 1, but because I skipped y, I'm just lining them all up. So the 3 goes below the 1 because it's an x. There is no y coefficient in the second equation, and then the z has a 1. Third equation, negative 1, negative 3, and 4. So this is a coefficient matrix. So these are important for different reasons, which we'll be talking about either in this video or the next one. I'm not sure how far we're going to go in this one. But the next term I want to talk about is an augmented matrix. So the augmented matrix now incorporates the constants that are on the other side of the equal. So we can't just throw them into the coefficient matrix because that's not what they are. So we augment the matrix. So I'm sure you guys have heard the word augment before, but we're going to make changes to this matrix. So now I'm going to keep the coefficient matrix as part of my augmented matrix. But now I'm going to draw a line. I just realized you guys can't see that. I'm going to draw a little line. And sometimes this is a dashed line. It depends on the textbook or the teacher or the website that you're looking at. And then on the other side is where the augmented portion is going to go, and it just so happens to be what these constants are from the original system. So 4, 5, and 0. And I'm going to close the matrix. So this is the augmented portion. It's what we've added after this line. So All they are the numbers on the opposite side of the equal sign when we go back to our system of equations. So it's pretty easy to do generally for this lesson, but what we're going to be using is it's an augmented matrix. So I'm going to do it one more time from the beginning. So I'm going to create a new system. So let's say 8x minus 2y plus z equals 1, 3x minus 4z plus y equals 2, 12y minus 3z minus 6 equals 0. So I want to rewrite this as an augmented matrix. All right. So hopefully you already caught the trick I was trying to play on you to write it before you can write it as an augmented matrix, which is built off the coefficient matrix. If you remember this last example, what has to be true about the system? Each of the equations should be in standard form. And if you notice, only the first equation is in standard form, x, y, z, with the 1 on the other side. So we need to create these the standard form of the other two equations here. So 8x minus 2y plus z, and obviously you can do this in your head. So 3x stays, but now plus y minus 4z equals 2, and down here there is no x term, that's okay. 12y minus 3z, so this one was almost perfect, but 6 isn't a coefficient. Negative 6 needs to move to the other side, so I'm going to add it to both sides and it becomes 6. So now that this is in standard form, I'm ready to create an augmented matrix. I'm just going to show you how to do that. All we do is we start by listing the coefficients, 8, negative 2, 1. And then I draw a line which kind of represents that equal sign. 1, 3, 1, negative 4, 2 goes on the other side. There's no x coefficient, or there's no x term, so there's a 0 coefficient here. 12, negative 3, and 6. So obviously you can tell this is one of the times where you could make a pretty silly error, just not checking to see if it's in standard form, so you want to do that first. So this is the augmented form. If I had instead of asking for the augmented form, just asked for the coefficient matrix, how would this be different? The augmented portion wouldn't be here. So this right here would just be with this gone. There's our coefficient matrix. So pretty easy, just talking about some terminology so that we can move on to the whole goal, which is to use one of these matrices to help us solve a system of equations. So before we get into that, let's talk a little bit more. We're going to go back to when we talked about solving these systems of equations, and we used those elementary operations where we were allowed to multiply an entire equation by a certain number, right? We can multiply it by some constant. We can add two equations together. We can subtract two equations. We can swap the order of the equations. So now I want to apply that process to working with matrices. So we're going to talk about row operations. So if you notice, when we now force these into a matrix, we've got these different rows here. So these rows represent the equations, right? So at 8x minus 2y plus z equals 1, we can see that that's represented here as this row, and this row. So when we work with matrices, we are allowed to do row operations, the elementary row operations. So we just insert that word row there because we're now talking about the matrix. So let's look at a couple. So I'm just going to create a silly little matrix here, but an easy one. So 1, 2, 3, 4, 5, 6. Let's make it a 3 by 3. 7, 8, 9. Okay, so here's our, I meant to be zooming out, not in. Here's our initial matrix, right? And let's say I want to perform a row operation on it. The arrow can't be that long. This board isn't that big. So we use some different notation here to do that. So let's say I want to change row 1. So row 1 equals 10 times the old row 1. So I'm just going to replace row 1 as the only thing that changes, and I'm multiplying everything in row 1 by 10. So obviously this is a coefficient matrix. It doesn't have the augmented portion. So what happens here? I get a 10, a 20, and a 30. But I haven't changed anything else. So this is the rule that we're using. So 4, 5, and 6 stay the same. 7, 8, and 9 stay the same. So what does it mean when we perform a row operation? So because this was a coefficient matrix, we can see what we're doing is changing the coefficient values for each of the variables. So if this was 1x plus 2y plus 3z, this has now become 10x plus 20y plus 30z. So we are changing the value of the coefficients. So here's where one of those elementary operations, now it's an elementary row operation, where I'm allowed to multiply a row by any constant. It could be positive, it could be negative, it shouldn't be 0. So any non-zero constant. So we're allowed to do that to any of the rows. We're also allowed to make swaps. So let's say we go back to this matrix, and I'm going to create a new rule. So we're going to go back to the original. I'm just going to play around with this one for a second. And let's say now I want to swap row 2. I'm going to swap it with row 3. So I'm capitalizing both of these because they're both going to change, but all I'm doing is swapping them. So row 1 remains the same this time. I'm not changing row 1. I'm only changing row 2 and row 3. I'm just changing their locations. 7, 8, 9, and then 4, 5, 6. So again, we can interpret this as we're swapping the location of the equations, right? So we haven't changed any of the coefficients, but we've just changed the order that they're in. So that's another elementary row operation. And we can also go back and do some pretty exciting ones. So let's say I want row 2. So I'm using a capital R to show that it's going to be a new row. So I'm changing row 2 by, let's say in this case, I'm going to write the rule down below just because I'm running out of room. So I'm going to say it's negative 4 times old row 1, because it's a lowercase, plus old row 2. So I'm using old row 1 and old row 2, but I'm creating a new row 2. So I'm going to go ahead and write in the 2 rows in this case that aren't changing. This is the only row that's changing, is row 2. So I'm going to take negative 4, I multiply it by old row 1, and I add it to row 2. So what's negative 4 times 1 plus 4? 0. Negative 4 times 2 plus 5? Negative 3. Negative 4 times 3 plus 6, what's that? Going to be negative 6. And that's it. So in this case, let's talk about what we've just done to our new row 2. So we've eliminated the x coefficient. So whereas this was 4x plus 5y plus 6z, we can now interpret it as just 0x, or no x, negative 3y minus 6z. So hopefully you have a little bit of foresight here, and you can tell what we're trying to do. We're trying to utilize those same processes we did with the system of equations to help us with solving a system using matrices. So using a matrix to solve a system of linear equations is called, recognize him, Gauss-Jordan elimination. So Gauss-Jordan elimination. So obviously Jordan built off of Gauss's ideas to help him or help develop a system here to solve a system of equations using his processes. So we're going to do that now. I'm going to take one of these. So we're going to solve a system. X minus y plus 2z equals 7. And 3x plus 2y minus z equals 10. Negative x plus 3y plus z equals negative 2. All right, so step 1, what do we do to use a matrix to help us solve a system of equations? So you want to build an augmented matrix. So step 1, build an augmented matrix. So make sure that these are in standard form. X, Y, Z, X, Y, Z, X, Y, Z. So we're good, and all the constants are on this other side. So if I'm augmenting, that's where I have the line, right? So coefficient, and then there's the line with the constants on the other side. So it's 1, negative 1, 2, 7. Second row, 3, 2, -1, and 10. Third row, -1, 3, 1, -2. All right, so once we have our augmented matrix, we're going to move on to step 2. So step 2, your goal is to get zeros in the entries. Remember, those are just the numbers in these matrices below the first entry. So what does that mean? If we want to get zeros in the entries below the first entry. So here's our first entry. I want zeros below it. So what am I doing? I'm eliminating the x coefficient in these two equations. So here's where those row operations come in handy, right? So how can we create zeros where the 3 and the -1 are? So I'm going to do that over here, and we'll come back to this page for our notes in a second. So here's our matrix, 1, -1. All right, so here's where I'm going to build those rules. So we draw an arrow just to show that we're changing the matrix. So I want row 2. I'm going to write a new row 2, -3 row 1 plus the old row 2. So if I have -3 times this plus this 3, what's going to happen? They're going to go away. It's going to equal 0. So because row 2 is the only thing that's changing, what may be helpful at first is just going in and writing what's staying the same. So those, row 1 and row 3 are not changing. Row 2 is the only one that's changing. So it's -3 times the old row 1 plus row 2. So -3 plus 3 is 0. And I have to do it to the entire row. I can't just change little pieces that I want. I've got to go through and change everything into what it should be. So, sorry, I got distracted. Now, so -3 times -1. -3 times -1 plus 2. What's that? 5. -3 times 2 minus 1. -7. -3 times 7, so -21, plus 10. Is that supposed to be a minus 10? I know, plus 10. So -11, right? Sorry, I worked this one out earlier in my notes, and I have a -10 there. So now we're just going to be winging it, which is fine. All right, so now let's talk about, we want to get a 0 here. So essentially, couldn't I just add row 3 and row 1 together? So if I add row 1 and row 3, I'm going to and replace row 3 with that, I'm going to get zeros down here. So here, because row 3 is the only thing that's changing, I'm keeping everything else the same. So -1 plus 1, 0. -1 plus 3, 2. 2 plus 1, 3. And 7 and -2, we've got a 5 there. So what we're doing when we are setting this up, by putting the zeros below the first entry, we're eliminating x's. All right, so I'm just checking to see that we are... Okay, so now what you can do is think of what we were doing when we're solving systems of equations, is I want to be able to get one of these two numbers to disappear. And normally we try to do a triangle, so I'm going to try to get 2 to disappear, turn into a 0. So is there a way to turn 2 into 0 while still keeping these zeros here? So I don't want to change the coefficients of x. I just want to change this coefficient of y, 2y, into a 0. So I want to change row 3. So let's find a way to change row 3. So if you notice, usually when we work on these problems, we just create a journey around the paper. So it's kind of like a snake action, and sometimes we can go a pretty long way. So I want row 3. I want a new row 3 that's going to create a 0 here. So let's talk about how to do that. So one of what if we tried to multiply row 1 by something and then add it to row 3? So the problem with that would be if I multiply row 1 by something and add it to row 3, I'm going to end up changing this value. So I don't want to do that. So I want to use row 2 because it's not going to change this value from a 0. So I can multiply this 0 by something and add it to this 0, and it's still going to remain a 0. The problem with this is if I want this to be a 0 as well, and I'm using a 5 and this has a 2 here, what are we going to have to do to make those go away? So we're going to have to swap some coefficients. So what if we said 2 times row 2, so that would be 10 here. How would I get a 0 here? I would subtract 5 times row 3. So 1, -1, and 2 remain. The first row remains. The second row remains. So now 2 times 0 minus 5 times 0. 0. 2 times 5 minus 5 times 2. 0. 2 times -7. I'm going to write that out down here. So 2 times -7 minus 5 times 3, right? So 2 times -7 minus 5 times 3, right? So -14 minus 15 is how we're going to get this -29 here. And I'm only writing this out. You can obviously use a calculator. We'll just do that now. So just because it gets a little complicated, right? So now we're doing 2 times -11 minus 5 times 5. So I'm just using these rules, right? So then we have -47. -47. So 2 times -11 minus 5 times 5. Okay, cool. Just making sure. So now that we did that, look what we've created. We have, if we go back to where we got this matrix from, we can say, I can take each of these rows and rewrite them as equations. So the first row is x minus y plus 2z equals 7. The second row is 0x, 5y minus 7z equals -11. 0x, 0y, -29z has to equal -47. So now we're at a place where we can just do our back substitution like Gauss came up with, right? So back substitution, we can solve for z. Once we have an answer for z, we plug it in, we can get an answer for y, etc., etc. So row operations are useful. By no means is it easy. By no means is it a shortcut. It's not the shortest way we have to solve equations, systems of equations, but it is a method. Now, we also can do these on your calculator, but what I want to do is we're going to try one more of these together, and then I'll show you some shortcuts and then there's a few more rules I need to sprinkle in. All right, so I hope it's okay that I know you guys can divide and back substitute. I just want to show you the process again. So let's say we're going to have a new system. Solve x plus z equals -2, -3x plus 2y equals 17, x minus y minus z equals -9. Okay, so when we use a matrix to solve a system of equations, step 1, make our augmented matrix. So this is x, we're skipping y and going to z, so 1, 0, 1. -2 is the augmented portion. So here we have x, y, and we don't have a z, so it's -3, 2, 0, 17. Here we have all three variables, 1, -1, -1, -9. So be careful with your signs, make sure you don't drop them. All right, so step two was to get zeros in the entries below the first entry. So the entries below the first entry, we want to get zeros there. So how are we going to do that? So I'm drawing my arrow. So clearly I need to do something with row 2 and row 3. So my new row 2 would be 3 row 1 plus row 2. And it's not uncommon to, because we have the same end goal for this first step, is to write two rules. So I'm writing one for row 2, and then I'm writing another for row 3. It can get a little confusing, so make sure you go slow. But how can we get a 0 here? Pretty easy. We can say row 1 minus row 3. Row 3 minus row 1, whatever works. We're just replacing row 3 with that. So I'm going to keep row 1, and now we're going to apply our rule to get a new row 2. So 3 times row 1 plus row 2. So I'm just multiplying all of these by 3 and then adding them to the row right below, and that's what my new row 2 is going to be. So we have 0, this would stay a 2, this would become a 3, so negative 6 plus 17, and then we've created a new row 2. Let's work on row 3. We're just row 1 minus row 3. 1 minus 1. Easy. 0 minus negative 1, positive 1. 1 minus negative 2. I'm sorry, 1 minus negative 1 equals 2. And then negative 2 minus negative 9 becomes a 7. All right, so step 2, get zeros in the entries below the first entry. And then our step 3, which I kind of abandoned these notes over here, but step 3 was get a second zero in row 3. So a second 0 in row 3. And generally we like that to be this one because we want to build a triangle of zeros and a triangle of coefficients is what the goal is, and we'll talk about why in a second. So we would like for that to happen if possible. All right, so that being said, I'm gonna get this 1 to turn into a 0. So now I ran out of room, so see how we're gonna go down, creating a snake, sassy snakes. All right, so I just need something to happen to row 3. So row 1 stays, row 2 stays, and we need row 3. We need this to be a 0. So again, think of the last example. We don't want to use row 1 because if we multiply anything in row 1 and try to add it to row 3, we're going to change the 0, which we just worked to get. So we don't want to undo the changes. So that means I need to do something to row 2. So what would I have to do to this number and this number so that I can add them together and it's got to equal 0? So what about row 2 minus 2 times row 3? And it's possible that there's going to be more than one way to go about these, so it depends on what your brain sees. So let's see if my rule works. So row 2, 0 minus 2 times 0, 0. Row 2, 2 minus 2 times 1. Yay! 3 minus 2 times 2. 11 minus 2 times 7. So the whole point of building this triangle here of zeros is to make it so that we can solve the last system, or the last equation in the system. So this is negative z equals negative 3. So that's easy. Z equals 3, right? And then we can back substitute. So the one above it is 2y plus 3z equals 11. Well, if z is equal to 3, we have 2y plus 9 equals 11. So that means y is equal to 2. And then finally, in this first equation, just going backwards, it's just 1x plus z equals negative 2. And I'm just back substituting. So x plus 3 has to equal negative 2. So x is negative 5. So the solution to the system is negative 5, 2, 3. All right. So, let's see. If we go back to this form, this triangular form here, where we try to get these zeros, there's a couple other special forms of matrices when we're using them to solve systems. And I'm not sure if Study Island gives you these notes or not. But there's something called echelon form. It actually is row echelon form. Row echelon form and reduced row echelon form. And the word echelon is a word for rank. So it's just a way to rank the rows. So essentially this is our goal, is to get them in row echelon form or reduced row echelon form. And what that looks like is almost what we've been doing, but it's where there's a 1 in the first entry, and then it looks like this. So we have this triangle that we just saw a second ago on our last example, but the difference is there's a diagonal of 1s. So 1, 1, 1. So this is row echelon form. And the letters that I used, A, B, C, D, E, and F, can be any constants. It doesn't matter what they are. To be in row echelon form, we need this triangle of zeros and a diagonal of 1s, starting with the first entry. Now, reduced row echelon form, so row echelon form we call this. So reduced row echelon form, here's its abbreviation, is almost identical, but now we have the 2 0 triangles. So we still have this diagonal of 1s, we still have this triangle down here of zeros, but then every other entry should be a 0 as well. So this is reduced row echelon form. And this guy right here, when something's in reduced row echelon form, this coefficient matrix is called an identity matrix. And we're going to talk a lot more about that in the next video, but it's called an identity matrix. And, yeah, we're going to do one by hand, and then I'm going to show you how to do this on a calculator. So we're going to solve a new equation, our new system of equations, by putting it in reduced row echelon form. So, there we go. Alright, so solve the system by putting the matrix in reduced row echelon form. So I'm not just lazy, this is like literally how directions would be given to you. I'm also lazy, but that's not why I'm doing it. So just for, since we haven't done one yet, I'm going to do a 2-variable system and show you what the difference is. Alright, so we've got a 2-variable system. The first thing we're going to do is put this in an augmented matrix. 7, 2, 9, 4, 5, 63. Alright, so our reduced row echelon form, if it is just a 2-variable system, would be, I ran out of room, so reduced row echelon form, 1, 0, 0, 1, and then over here, like this. So the good part about this is when something's in reduced row echelon form, when you've got an identity matrix here, think about what it's saying. 0x plus 1y equals whatever this number is. X plus 0y equals whatever this number is. So reduced row echelon form just takes away that back substituting, so you don't have to do any back substituting. Alright, so now, forgot to say that, so I'm going to go backtrack. Alright, so the first thing I'm going to do is I want, and we haven't seen one like this before, I need a 1 in the first entry. So I need to make this a 1. Well, what's the easiest way to turn a number into a 1? Divided by itself. So our new row 1 is going to be 1/7 of the old row 1. 7 divided by 7, 1. 2 divided by 7 is just 2/7. 9 divided by 7, 9/7. Ew, fractions, gross. Alright, second row, I didn't touch it, so I'm leaving it alone. Now, here's where we go back to those other rules. Now we want zeros below the first entry. So for reduced row echelon form, our new first step is to make sure the first entry is a 1 before we start putting zeros in below it. So now how can I turn this 4 into a 0 So I can't divide by anything for that to happen. That means I need to reference another row. So my new row 2 is going to be negative 4 row 1 plus row 2, or 4 row 1 minus row 2, whatever you're into. So negative 4 plus 4. Oop, I'm sorry, I didn't do what I told you guys to do. So I'm just rewriting row 1 because I'm not changing it. So negative 4 times old row 1 plus row 2. So here's where it gets a little weird. So we have negative 4 times row 1. So let's just do this. So negative 4 times 2/7, right? Oops. Plus row 2 plus 5. So that's ugly. So how do we change that to a prettier number? Change it to a fraction. So 27/7. And I'm going to do the same thing now. So negative 4 times 9/7 plus 63. Ugly number, make it a fraction. 405/7. Okay, so now I want it in reduced row echelon form. So it should be 1001. So this may be a little bit strange, I don't know, but you want to focus now on putting 27/7, turn it into a 1 before you try to make this into a 0. So turn 27/7 into a 1. So let's think about a way to do that. So if I want a row 2, a new row 2, and I want this to be 1, well, how did we get a 1 previously? We divided that number by itself. So I'm dividing 27/7 by 27/7, which really means I'm multiplying row 2 by 7/27. I'm multiplying by the reciprocal. So I'm not changing row 1. I am changing row 2. So if I multiply 0 by anything, it's still going to be a 0. 27/7 times 7/27 is 1. That's what I wanted. Yay, we did it. All right, so now I need to multiply 405 divided by 7 times 7/27. So for the purposes of this, we're gonna do a little cheating. So we still have 405 divided by 7. I'm multiplying that by 7/27. Look at that, a nice pretty number. It's almost like I designed it that way. All right, so we're very close to getting this in reduced row echelon form. We have a 1 and a 0. Now I need a 0 here, and I'm going to keep my 1. So how can I change 2/7 into a 0? So anytime I'm trying to get a 0, I'm going to have to reference another row. So now I'm creating a new row 1 because my row 2 is perfect. So my new row 1, to make 2/7 equal to 0, I can say negative 2/7 times row 2 plus row 1, right? Because I'm going to try to multiply 0 by a number, so it's still going to stay at 0, and I'm going to keep that 1 there. That's what I wanted. And now, if I do negative 2/7 times 1 plus 2/7, it's 0. And because I know, let's go ahead and use our calculator. Let's get a little more light. Is that better? Okay. Well, crap, now I forgot what it was. Oh, so negative 2/7 times 15, right? Negative 2/7 times 15 plus 9/7. Negative 3. So again, the good part about this is now in reduced row echelon form. It's pretty common to write that once you've done it. So we did it, right? We put it in reduced echelon form, but I need to go back and solve the system. Well, we actually did that. So now this first equation says 1x plus 0y equals negative 3. That's it. X is equal to negative 3. 0x plus 1y equals 15. So y equals 15. So this is our solution. The solution to this system is negative 3, 15. All right, so now I want to show you that your calculator is capable of doing this stuff for you. So if you hit your math button, I think, probably should have looked at this before I did this video. I need to put in a matrix first. So yeah, see matrix? Duh. So second matrix. And there's some that are in here. You may have some that are in here. I'm going to go and edit one. So I'm going to edit. And so if you see, if you want to edit, you can choose the dimension. So 2 by 2 or 3 by 3. So when we use this to solve a system of equations, we actually put the entire augmented matrix in. So, this, remember, it's row by column. So the augmented matrix, 2 rows, 3 columns, 2 by 3. And then I'm going to go and just change the coefficients. 4, 5, 63. Just like that, okay? So let me check to make sure before I clear. Okay, so now I'm going to go off, and then I'm going to call up this matrix. So I just did second matrix again. I'm calling up, calling up the matrix. So I want to use matrix A. So I just push enter when it's on matrix A. And then I'm going to go to, why do I keep doing that? Second matrix math. So I'm doing matrix math. Oh, that's right, I'm using this old calculator. So I'm going to have to reverse the order of this, of course. Of course. So back to matrix math. So now this may be done. All right, reduce row echelon form. Reduce row echelon form. Now I'm going to call up matrix A. This may not work because this is not my normal calculator. Oh, it did it. Look at that. So if we tell it to take that original matrix, but we want it in reduced row echelon form, just like it asked, look, it gives us the answer, right? This is what we got to at the very end. So it can give us this information. So reduced row echelon form is really nice because it just barfs out the answer. So x equals -3 and y equals 15. So if we go back to that 3 by 3 one, 3 equation, 3 variable one, so you can go back in the video, but, or let's just try another one maybe that we don't have an answer for. Because why not? We have all the time in the world. Let's solve by reduced row echelon form. So here's our system. X plus y plus z equals -4. And 2x minus 3y plus z equals -1. 4x plus 2y minus 3z equals 33. So if I want to solve this one by hand, we absolutely can. There will be a lot more row operations than the one we just saw because the system is bigger. But we can create an augmented matrix. Make sure it's in standard form. And then throw all these bad boys in. And then now I'm going to rely on my calculator. So the first thing I need to do is put this problem in. So go to your matrix. We can use matrix A again. You see you have the capacity, to store a whole bunch of them. So whatever you want, and when we get, if you go back to the previous video where you had to operate with matrices, you could do it in here as well. So I'm going to go ahead. I'm just going to reuse matrix A. I pushed the wrong button. Glad you guys are here for this. So let's go back to edit matrix A. So now, what are the dimensions of this? So it's row by column. So, number of rows by number of columns. So this is a 3 by 4. So I know it may seem strange that, how are we accounting for this augmented portion? Just don't worry about it. So 1, 1, 1. I'm just going straight across. -4, so that it leads me that way. And -1, and 4, 2, -3, and 33. All right, so now we've got this matrix in there. So I want to go back. So second matrix, call up my menu. I want to do some matrix math, right? So there's a lot of different things in here, and we'll talk about not every single one of them, but quite a few of them. We want reduced row echelon form. And then I put this all in matrix A again, hit enter, and without doing any of those ugly row operations, it puts this in reduced row echelon forms. So it's 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And then the answers are going to be the augmented portion. So it's 3, 0, -7. X equals 3, Y equals 0, Z equals -7. So the solution is the ordered triple, 3, 0, -7. Easy peasy, lemon squeezy.